Okay. In this session, we're going to go on to Bayes' theorem. Now, remember what we did before when we had conditional probability. We said probability of A given B is probability of A intersection B divided by probability of B. Okay? And then we saw that in some problems it would be convenient if we rewrote the numerator, the probability of the intersection, using the multiplicative law. And we rewrote the denominator using the law of total probability, right? And that was basically Bayes' theorem. So we've already done that, okay? Now we're going to give it a name, all right? So let's just review basically how we got that, okay? So we have this definition for conditional probability, right? And you can see that if I have probability of A intersection B, I can bring probability of B over here. So probability of A intersection B is probability of B times the probability of A given B. Okay, we've discussed that before. That's what we call the multiplicative rule, right? And that's what's been done down here. So sometimes probability of the intersection is a bit more difficult, and for some reason this calculation may be easier. Okay. Now we also had the idea of a partition. So we have we can partition the sample space S into a bunch of sets. Their union is all of S, and their pairwise intersections are empty, right? So that these BIs don't overlap with each other. So you can think of S as being broken up into these BIs. Okay? And we saw that if you had that, then if you took any A in the set, the probability of A can be given as the sum of the probabilities of A intersected with each of the BIs. Right, so let's say we have a set S, and it's got a B1, a B2, and a B3, and then we have our A. Well, we say, what's the probability of A? Well, we can break it up into pieces. It's the part of probability of A intersection B1 plus the probability of A intersection B3 plus the probability of A intersection B2. You take the probability of A from each one of the intersected with each one of these partitioning sets. And sometimes that's easier if you choose your BI in a good way. It can make your calculations easier. Okay? So now, let's suppose that we have these BIs, B1 up to Bn. They're a partition of S. The probability isn't 0 for any of those. There's no need for such a set in your partitioning set. And there's some event A with a non-zero probability. Okay? Then what we're going to do is we're going to come up with something that relates the probability of A given BK with the probability of BK given A. Okay? Because sometimes you have this one, but you actually want that one, or you have that one and you want this one. Okay? And we're just going to do the same thing that we've been doing before. We take the definition of conditional probability, we rewrite the numerator, which is a probability of an intersection with the multiplicative law, and we rewrite the denominator using this idea of a partition and total probability. Okay? So we're going to start with the probability of BK, one of the partitioning sets, given A, is the probability of BK intersection A divided by the probability of A. Okay? We're going to rewrite the top there with the multiplicative law, and we're going to rewrite the denominator there using total probability. Okay? All right? And so, okay, so here's probability of A on the bottom. And because the BIs were a partitioning set of events, this can be rewritten as the sum of probability of BI intersection A. Okay? And you would want to do that maybe for some reason. Writing it this way is easier than writing it that way. Is there a question? Okay. All right. So we replace the bottom here using this total probability idea. And now so the probability of BK given A is equal to probability of BK intersection A divided by the probability of A, which has been rewritten using this partition and the idea of total probability. Okay? All right. So now we turn our attention to the numerator. Well, the numerator is probability of BK intersection A, but by the multiplicative rule, this is probability of BK times the probability of A given BK. So I'm going to replace that, this numerator, by this different way of writing the numerator. And now we have, on top, we have probability of BK times the probability of A given BK divided by this probability of A. Yes? Yeah. So we're going to rewrite the bottom here. Right? Oh, sorry. We're going to rewrite the top here, the numerator, with this. And we've already rewritten the probability of A this way. Okay? And now, okay, so now we have finally what we want. Probability of BK given A is probability of BK times the probability of A given BK. That's probability of A intersection BK intersection A divided by the probability of A, which has been rewritten using total probability. Okay, now, so quite often, this is what you're interested in, probability of BK given A, but what you've been given might be probability of A given BK, right? And so this is the way of, this gives us a rule for calculating what we want from what we might have been given. Okay? And if you ever forget the formula, you know where it came from. You can always work that out. Okay? So this is Bayes' rule or Bayes' theorem, and I think we've used a similar idea before. We just didn't give it a name. Okay, so now we have it. We're seeing it again, and now we can we can go back and look at a problem that we might have done before. Okay? So, supposing that 0.1% of the population have the dreaded disease DS, the test for DS gives a positive result with probability 98% when the disease is present, and it gives a negative result with 99% probability when the disease is not present. Okay? We had a similar problem before, and we're going to do it using Bayes' rule this time. Okay. So what's the probability that someone who tests positive has the disease from this information? Okay, when someone has the disease, there's a 98% chance of a positive test. When someone does not have the disease, there's a 0.99 probability of reporting that the person doesn't have the disease. Okay? What we want to know is, what's the probability that someone who tests positive has the disease? We haven't been given that. Right? Okay. Okay, so we need some notation for doing the problem. Let D be the event that the person has a disease. Let T be the event that the test shows positive. What we've been asked for is, what is the probability that the person has the disease given that the test is positive? All right, we turn that into the language using the, using our, we've been given in words. We write that mathematically. We'll write it mathematically like this. So let's say the probability that someone has the disease is, in the general population, is 0.001. We'll say that the person who has the probability that the test gives a positive result for a diseased person is 0.98. And the probability that the test gives a negative result, which is the complement of giving a positive result, given that the person doesn't have the disease, the complement of D, is 0.99. So let's say that we have this information. Okay? Okay, so we have probability of T given D, but I want the probability of D given T. So I recall that Bayes' rule can help me with problems like this. Okay? Okay, now I might want to calculate some complements while I'm at it. If the probability of disease in the general population was 0.001, then the probability of not having the disease in the general population is 0.999. If the probability of having the disease is, the probability of testing negative when you have the disease is 0.02. Okay? And the probability then of testing positive when you don't have the disease, a false positive, is 0.01. Yeah.
सर मुझे ये नहीं समझ आती जब probability of A given T को हम 1 minus करते हैं, so 1 minus probability of A given T, why does उसका result is the complement of only A? Like to find the probability of T not given D, हमने finally 1 minus probability of T given D किया.
जी.
तो इससे सिर्फ T complement क्यों? Why not D also? Why is the first one also?
Okay, so if you think about it, we have intersections going on here, right? So the and then you're dividing by the probability of some set. So if you're looking at the complement, so kind of like this. Say here. So let's say B1 and B2 are partitioning, and you're looking at the probability of A, or you're looking at the probability of A complement. Then you're still dividing by the same. You should still be dividing by the same probability factor. So, okay. Or you could go back to the definition and you'll see that that's the way it goes, right? From the definition of conditional probability. Okay. All right. So I want the probability of D given T. So I'll just write that down. I know what that is. The formula for that is the definition of conditional probability. So that's the probability of D intersection T divided by the probability of T. And then I say, well, wait a second. I haven't been given probabilities of any intersection in this problem. Or in the data that I have, I don't have the probability of an intersection. So, okay, I can rewrite the probability of the intersection, right? Probability of T given D is probability of T intersection D divided by the probability of D. So I multiply by the probability of D, and I get the probability of this intersection. Okay? Now, I don't have probability of T, but I can think of D and D complement, partition S, or an event and its complement, always partition S. Okay? Well, non-empty events, always partition S, like this. So I can rewrite probability of T as a probability of D times the probability of T given D, plus the probability of D complement times the probability of T given D complement. Okay? I've kept my multiplicative rule and my total probability idea in my head. So basically I've rederived the Bayes rule. I don't always have to remember every formula. I can just, I can derive it, and I'm doing it this way because I'm keeping in mind the information that I have and the information that I can readily calculate. I'm keeping those in my mind, okay? So now we have it written in this form. All right then, is that enough? Yeah.
Denominator to second value of which
You're talking about this value? This one. Okay. Well, okay, so if we're given that the probability, that the general population has a particular probability of a disease, then we should be able to find out the complement of that, right?
So to peri value, that is the probability of D intersection D, right?
That's the probability. Yeah, up here, that's the probability of D intersection T, yes.
Or denominator to the first value, that's the same.
And yeah. So what you will see is that one of the terms at the bottom will be the same as the numerator.
But since you other value, how does adding that only give the probability of D that forever?
Well, this is okay. If you have S and you have an event D and you have its complement in S, D complement, then they automatically partition, then that partitions S. Okay? So D and D complement partition S, and then this is given by total probability. This, right? So here's your T. So the contribution to the probability of T, where T lies in D, and this is the part of T that lies in D complement. So we also add the probability that's coming from that part. Okay, so and then we put those two probabilities together, and that gives us the probability of T altogether. Okay, so now we've been given all the numbers, and we put those numbers in, and we get this value. Now, a lot of people, if we look at what we originally given, right, they would read, oh, okay, so a positive result of 98% when the disease is present, and they interpret a negative result of 99%. So they think that if the test is positive, there's a 90-something% chance that the person actually has the disease. Okay? Okay? Now, and unfortunately, doctors often do this, right? So there have been repeated surveys. Doctors have given this thing, and their estimates are in the high 90% chance of the person having the disease. Okay, so 0.1% of the population have DS, 0.001, right? Now, our result is considerably higher. Having the test read positive increases your chance of having the disease many times, right? Well above that of the regular population, right? But it doesn't make it 99% or 98%, okay? So that's something to keep in mind, right? When results of medical tests need a little bit of interpretation before you take any serious action based on them, okay? All right. Let's try a second example. Okay, we can think our way through this one. So we have a supplier of positronic brains. We have 3 suppliers, right? We buy our positronic brains from 3 different suppliers, okay? I'll call them 1, 2, and 3, okay? 3% of the brains supplied by supplier 1 are defective. 5% of the brains supplied by 2 are defective. And 4% of the brains supplied by supplier 3 are defective. Okay? So, in terms of conditional probabilities, what have I been given there? Can someone tell me one thing that I've been given in terms of conditional probability? Yeah.
And the probability that the brain is defective given that it's supplied by...
Yeah. Okay. Right. Okay. So what we might want is, the information we might want is, given that something is defective, what's the probability that it came from supplier number 2, let's say? What we've been given is that given that it's coming from supplier 1, the probability of a defect is 3%. Okay. All right. All right, so let's say we order 5,000 brains from supplier 1. We order 3,500 brains from supplier 2. We order 2,000 brains from supplier 3. Okay? And then we don't keep them separately. We mix all the brains together in our warehouse. Okay? If the brain is taken from the warehouse at random for testing, what's the probability that it's defective? Can you think of how to do that? Okay. What might I use to work out the probability that any random brain selected will be defective?
Sir, currently what we have is like defective given 1 or defective.
Yeah, right. So we have defective given supplier 1, defective given supplier 2, defective given supplier 3. Okay. I don't know what the probability is that a given brain is defective right now. I have to calculate it. I am given some information concerning the defectiveness of brains given by the different suppliers. Right, okay, so I can think of it this way. Here's S. Right? So here's the event that the brain comes from E1. So from supplier 1. We'll call E1 means coming from supplier 1. Then there's the event that the brain comes from supplier 2. Then there's the event that the brain comes from supplier 3. Right? And that partitions the sample space. Because some these are non-empty sets, right? And a brain can't come from two suppliers, it's coming from a single supplier. So these events, E1, E2, and E3 are partitioning the set. And then some of these are defective, some of these are defective, and some of those are defective. Okay, so what does that remind you of? Probability of D given, okay, yeah, okay, so almost, so you're almost right. So the probability of when you have a partition and you've got a set like this, D, right, you can take when you have a partition, you can take the probability for this intersection plus the probability of this intersection plus the probability of that intersection, right? So this is the probability of D intersection E1 plus the probability of D intersection E2 plus the probability of D intersection E3. Yeah, E1 means supplied by supplier 1, E2 means supplied by supplier 2, E3 means supplied by supplier 3. Okay? Now, have I been given that information? Well, I haven't been given that information directly, so I might have to massage this a little bit. I have to do a few more steps before I can start plugging in numbers. Okay, what have I been given? I've been given the probability of D given E1. Probability of D given E2 is there. Probability of D given E3 is there. So I rewrite this as probability of D given E1 times the probability of E1 by the multiplicative rule, right? I rewrite the probability of the intersection in terms of a conditional probability. Okay? Now what about this one? Probability of D given E2, that's not quite what I want. That's not quite the intersection. I have to multiply by probability of E2 plus the probability of E3 times the probability of D given E3. Okay? Now, do I have... Well, okay, so I was given the conditional probabilities up front, and what else was I given? Right? I was given that this is how many brains came from E1, how many came from E2, and how many came from E3. So if I take the fractions divided by the total number, that will give me the probability that a particular brain came from E1 or from E2 or E3. Okay, so this is the way to do it. And this is basically what we call total probability. Okay? Okay, so in the notes I wrote S1, S2, S3. That's probably a bad notation since S means sample space for us, right? But okay, using this bad notation. So let's say S1 means from supplier 1, S2 means brain came from supplier 2, S3 means brain came from supplier 3, and D will mean defective. Okay? The total is 10,500 brains. Okay? So 5,000 of the 10,500 brains came from S1. So that's the probability that a selected brain came from S1. 3,500 out of 10,500 brains came from S2. So the probability of S2 is this fraction. Probability that a selected brain came from S2. Okay? 2,000 of 10,500 total brains came from supplier number 3. So the probability that a selected brain came from supplier number 3 is this fraction. Okay? Is that okay? All right. So then, and we recall that what we were given, right? We were given that 3% of the brains from S1 are defective. In our language, that's the probability of D given S1 is 0.03. We were given that 5% of the brains from S2 are defective. So in our language, that's the probability of D given S2. And we were given that 4% of the brains from supplier 3 were defective. And in our language, that's the probability of D given S3 is 0.04. Okay, so with these numbers, probability of S1, probability of S2, probability of S3, and these conditional probabilities, we have everything that we need to apply total probability to get the answer. And so if we plug in all these numbers that we've been given and that we've calculated, well, we'll get some number. Okay? That's the probability. Little under 4%, there's a little under 4% chance, probability, that a randomly selected brain from our warehouse is defective. Let's continue that. So now I can ask the problem. Suppose that a randomly selected brain is defective. What is the probability that it came from supplier 1? Right. So we are asked that the probability, what's the probability that a brain came from S1 given that it's defective? Okay, what did we have? We had D given S1, but we don't have probability of S1 given D, right then. Okay, but I recall that this Bayes approach allows me to, if I've been given things like D given S1, S2, S3, then I can find probability of S1 given D, S2 given D, and S3 given D. Okay? So once again, I'm probably not going to...
Sir, S1 given D looks small,
No, we were given D given S1, but we're being asked for S1 given D. Right? Finding S2 given D, finding S3 given D, it'll be the same approach, right? So, okay, so I can never remember the formulas, okay? Or so I just remember a few formulas and then I can get the other ones, they'll fall out. Okay, so once again, conditional probability. This is S1, probability of the intersection, S1 intersection D, divided by the probability of D. Okay, I've already found the probability of D, right? Okay. Okay, I don't have probability of S1 intersection D either, right? Okay, but I do have some conditional probabilities involving S1 and D. And I have the right? So this is the probability of D given S1. That I do have, right? That would be probability of D intersection S1 divided by the probability of S1. So then I multiply it by the probability of S1. And that gives me probability of S1 intersection D. Okay, well, that's just the multiplicative rule. If you can remember that, that's great. Otherwise, you can derive it. Divided by the probability of D. Now, I've already calculated that, I think, but if you wanted to show off, right? You would say that this probability of D is the probability of D intersection S1 plus the probability of D intersection S2 plus the probability of D intersection S3, because the events S1, S2, S3 partition S. And then you'd say, okay, wait a second. I don't have these, but I have conditional probabilities which involve those events. So what do I do with probability of D intersection S1? Okay, so it's probability of D given S1 times the probability of S1. So I'm rewriting the intersection. Okay, so it's a similar pattern then. Probability of S2 times the probability of D given S2 plus the probability of S3 times the probability of D given S3. All right, and so the definition of conditional probability and the idea of total probability give me this nice little pattern here. And as a check, I check and I see that one of the terms in the denominator here is the numerator. Yeah?
So just clarify, can you get probability of S1 intersection D is equivalent to probability of D intersection S1? Like if you switch the intersection.
Yeah. Yeah, so intersections, it doesn't matter how you write A intersection B or B intersection A, right? Okay? So we already worked this out, but if we forgot that we had done that, we could use this. And now we have everything in terms of things that we've been given. And as I said, quite often you have A intersection BI, but what you want is probability of BI given A, right? So Bayes' rule can help you do that. Right, and okay, so this is this business that we've done here. And we plug all the numbers in. And if I've done my arithmetic correctly, you'll get about 0.37. Okay. Okay, any questions about that one? Okay, so that was Bayes' rule. a very important idea in probability and statistics is the idea of a random variable. Okay? And the convenience of the random variable is that given, say, a sample space, your sample space could have all sorts of things in it. You could have text, you could have images, you could have whatever, right? But it's easier to work with numbers, right? So when you're, we define random variables, which are maps from the sample space to real numbers, right? And then we tend to work with those random variables a lot. Okay? So a random variable is supposed to assign to each element of the sample space a real number. Okay, so we'll do a few examples of how we do that. Okay. The convention that I will try to follow is this. Random variables usually will be given by a capital letter. The value that the random variable takes will be given by the corresponding lowercase letter. Okay? So capital X is the random variable. It's a function from the sample space to the real numbers. Small x is the value that the random variable capital X is taking. Okay, so let's do a simple one. I'm going to roll a die once, a fair six-sided die once. So you have a sample space which consists of roll to 1, roll to 2, roll to 3, up to roll to 6, okay? Now, I can think of infinitely many functions to define on that sample space, but here's one. I'll say that there's a random variable y, which is a function, from the S to the reals, and it's going to take the value 1 if the result of rolling the die was an even number. And it's going to take the value -1 if the result is an odd number. Okay, so that's our first definition of, or the first example of a random variable, right? For every single element of the sample space, there's I can tell you that if you rolled a 3, that's an odd number, so y will take the value -1. Okay? Okay. So this would be one way of representing it. If you had these inputs, 1, 3, and 5, y is taking the value -1. If you had these inputs, roll to 2, roll to 4, roll to 6, then y is taking the value +1. Okay? So, we run this experiment, we roll the die. What is the probability, right? The experiment gives random results, so y is also random. So we can talk about the probability of y taking a particular value. So what's the probability that y takes the value -1? Why? 1/2, why?
Probability of rolling odd.
Yeah. The probability that y takes the value -1, how does y get to be -1? You rolled an odd value. So that's the probability of rolling an odd result. And the probability of rolling an odd result for a fair six-sided die is 1/2. Okay? Good. So y takes the value -1 if and only if the roll resulted in an odd number. The probability then is, can be given by this. The probability that y takes the value -1 is the same as the probability of this event, and the probability of that event is 3 outcomes, equal probabilities out of 6 outcomes, so 3 out of 6. Is that okay? All right. What's the probability that y takes the value +1? Again, 1/2. Okay? So, the probability that y takes the value +1, well, it takes the value +1 if and only if this event occurred. The probability of that event is 3 outcomes out of 6 equally likely outcomes. Okay? Okay. What's the probability that y takes a value which is not +1 or -1? What's the probability that y takes the value 37? 0. Because y never takes that value, so the probability that it takes the value 37 is 0. I would say that, okay, I would say that right. It's not, 37 is not an output of y. Okay, so this is one way of summarizing that information. Okay? The probability that y, the random variable y, takes the value small y is 1/2 if y equals -1. It's 1/2 if y equals +1. And there's 0 probability that it takes any other value. Okay? So this is the way that I will commonly write the information about the probability of y taking, or the probability of a random variable taking various values. All right, I'll write it something like that. Okay? Okay. Let's try another one. Let's say we roll a fair die, and we record the results 100 times, and we record the results of each roll. Okay? The sample space has 6 to the 100 elements, so I'm not going to write it out. Okay? So let's say for some reason we are interested in how many, when you roll this 100 times, how many 6s did you get? For some reason we're interested in that. So we could let the random variable x be the number of times that a 6 occurs. Okay. So what's the probability that x is equal to 0? I mean, in principle, you could roll a die 100 times and never get a 6. Right. The probability of not rolling a 6 once is 5 to the 6. The probability of not rolling a 6 100 times is 5/6 to the 100. Okay? Because the rolls are independent, right? Okay, so that's, well, that would be small. Okay? What's the probability of rolling 6 times? What do you think? Well, might have to think about that a little bit. Right? Okay, so we're going to discuss this problem in some detail a little bit later. So let's skip the entire discussion for now. I just want you to note the way we write this. Okay? K can take values 0, 1, 2, up to 100. So for a given K, taking those integer values, the result is n choose K, here n is 100. P to the K, 1 minus P to the 100 minus K. The probability that X takes any value except 0, 1, 2, 3 up to 100. Probability that X takes the value pi, for example, is 0. Okay? So this is the way that I would write this. You have something for all the allowed values of K, and you say that it's 0 otherwise. Okay? You should get in the habit of writing it this way, because it's going to be important later. Okay. All right. Okay, so another experiment. So there were only 101 values, right? But here there are infinitely many values. So I'm going to measure the velocity of a gas. So there are infinitely many vectors that could be, in principle. Right? And then I've measured the velocity. Given the velocity, I can calculate the kinetic energy. Right? Kinetic energy is 1/2 mass times the square of the speed, right? So the sample space are these infinitely many vectors. The random variable, which are random outcomes. And then the output, then the function x is the kinetic energy, which given any one of these vectors, you can map it to a real number, 1/2 mv squared. Okay? Yeah, so in general, velocity is a vector, right? So I measure the velocity of a molecule, and then I calculate its kinetic energy as 1/2 mass velocity squared. Okay? So that's a random variable. It's a map from the sample space of all the allowed velocities to the real numbers, and that real number I'm calling the kinetic energy. Okay. Okay, so we have this terminology of discrete and continuous random variables. The dice rolling problem, that's an example of a discrete random variable, right? And this problem here with the kinetic energy, that's an example of a continuous, what's called a continuous random variable. Okay? So basically the idea is that if the sample space is the size of the integers, or less than the size of the integers, that we call that sample space discrete. And then we say, yes?
So by integers you mean like the set of integers?
Yeah, the set of integers. If you had, say, a sample space which was the size of the integers, had the cardinality of the integers, or some smaller set, we say that that's discrete. And then the random variables defined on a discrete sample space are called discrete random variables. Okay? On the other hand, if you have a sample space which is continuous, that is, it has the cardinality of the number of points in a line segment, then it's said to be continuous. And then we say that the random variable, which is defined on a continuous sample space, we say that that random variable is continuous. Okay? You'll see a few examples of these. You'll be fine with the. No, the rational numbers have the cardinality of the integers. Oh, the irrational. Well, okay. If it has the cardinality of a line segment, then it's continuous. Okay, so this business about the molecule of an ideal gas is the sample space is continuous. And so any random variable defined on that is said to be a continuous random variable. Let's break at this point. Okay. Yes?
Discrete random variables are not infinite, or can they be infinite?
Yes. Yes, discrete random variables can be infinite, but they have the cardinality of the integers, which are infinite. They don't have the cardinality of the reals, which are somehow more infinite.